Hello everybody, and you've made it to Unit 6. This entire unit is all about right triangles and different properties of right triangles, so unfortunately you are not done with triangles yet. But after this we should be ready to go to move on to different shapes. However, we're going to focus on different properties of right triangles. Before we can do that, we need to really learn how to simplify radicals, and then we're going to do a quick review of the Pythagorean Theorem. So let's review how to simplify a radical. So when I say simplify a radical, I want to make sure that there's no perfect square that exists underneath the radical. So let's take a look at number 1. So I have the number 72. Now there are many ways that you can go about simplifying a radical. I'm going to show you the fastest way. What I want to do is go through the number 72 and identify perfect squares that could possibly divide into it. So underneath the number 72, the closest one is 64. But if you did 72 divided by 64, you're going to get a decimal. So then I'm going to move down to 49. Well, again, 72 divided by 49 gives you a decimal, so I'm going to move on now down to 36. Well, what I notice is that 36 divides into 72 evenly. It divides into it and it creates, let's see if I can get this right, 36 times 2. So one of the numbers is a perfect square and the other one is not. Again, this is only one way to do it. There are multiple ways to do it, just so you are aware. This is the fastest. So what I know now is with radicals, when you have two square roots like that, we can then separate them into two separate radicals. And anything that's a perfect square, go ahead and take the square root of it. So in this specific case here, the square root of 36 is a positive 6, and the square root of 2 cannot be simplified any. So that's done right there. And that's simplified as far as possible because the 2 doesn't have anything in there to simplify it. Looking at the one on the right, same process. Now I've already gone through and simplified the square root of 72, but the thing here to remember is that we have the 2 on the outside. So that's what makes this problem different. So I already know 72 is going to reduce down to 6 square root of 2. Now the thing to remember here is that this is one big multiplication problem, even though it doesn't look like it. In between this 2 and the square root of 72 is multiplication, just like in between this 6 and square root of 2 is multiplication. And so after you simplify a radical down as far as you can then take the 2 numbers on the outside and simplify those by multiplying them. So the way that we finish this up, it'll be 12 square root of 2, and that would be finished. So moving forward, we're going to be doing a lot with square roots, with special right triangles, and some stuff with Pythagorean Theorem. So you want to be aware of how to do that. The other thing you need to be able to do is square a square root. The key thing here is, now a lot of you can probably type this into your calculator and get a number, but let's talk about how to do it by hand. So when I do something with an exponent of 2, that means I'm multiplying the same thing by itself. So essentially what I have here is the square root of 7 times the square root of 7. Well, just like we did up in problem number 1, I can separate things. I can go ahead and put these two things together. So this is the same thing as saying the square root of 49, but we all know the square root of 49 is equal to 7. So whenever you square a square root, you get the number that's underneath the radical. And when we do the Pythagorean Theorem, we're going to be squaring square roots. So please make sure you've followed along. If not, please have someone help you out. So let's take a look at number 4. This is different now. So on the left-hand side here, the square root of 7 and the 2, the exponent of 2, those are inverses of each other, so they cancel each other out. Problem with number 4 is we have this 3 on the outside. So when we do this, keep in mind that this is 3 square root of 7 times 3 square root of 7. So we've already gone through and shown that square root of 7 times square root of 7 is 7. But let's again review. This is one big multiplication problem. So let's go ahead and rearrange this around. This is the same thing as 3 times square root of 7 times square root of 7. And so what I notice here is 3 times 3 is 9. Square root of 7 times square root of 7 is 49. And then finally, square root of 49 is equal to 7. So then I can go ahead and multiply that and get the number 63. So whenever you're squaring these guys, you should never end up with a radical. A very common mistake is to forget to square the 3 here. So please make sure you're paying attention to when you're doing with that. Okay? Alright, so let's go ahead and actually talk about the right triangles. So this is our very first one with the Pythagorean Theorem. You probably have heard this in the past. What we have here is we have two legs, A and B. And what the actual Pythagorean Theorem says is if the triangle is a right triangle, then the sum of the squares of the sides is equal to the hypotenuse squared. So we saw the A and B are the legs. C here, that's across in the right angle. That's always our hypotenuse. So the actual thing here is A squared plus B squared equals C squared. Now C is always the largest number because it's crossed from the biggest angle. The other two angles are going to be acute angles, so A and B are always going to be smaller. So we always make sure the hypotenuse is in C's spot. Okay? let's go ahead and do some examples with this. So here's our first one. We're going to go ahead and solve for the hypotenuse. The big thing here is to identify what you're solving for so you know where the unknown is going to be. So I'm going to substitute this into Pythagorean theorem. We have a squared plus b squared equals c squared. I substitute them in, square everything in, and then I add them and take the square root. So the nice thing about this one is we got 100, and so the perfect square of 100 is 10, so that was really nice. That's not always going to happen. So let's take a look at this one here. Now the difference is now I'm not looking for the hypotenuse because the hypotenuse already has a value, so I'm looking for a leg. Now it does not matter if you want to put x in for a or x in for b, since addition is commutative. It doesn't matter where you put it in. So for here, I'm going to go ahead and square it. Now in this case, I'm going to subtract the 9 from the 25. Unlike the one on the left, I add them together. So when I subtract them, I end up with 16, and the square root of 16 is 4. Look at that pretty number. All right, let's hope this one should be an example where that's not the case, where we won't have a nice pretty number. So in this one, I'm looking for the hypotenuse. So the c is the open spot here. So I have 4 squared plus 6 squared equals x squared. Square them and add them, and I get 52. So we're going to take the square root of 52, and we're going to try to find, well, what perfect square goes into it. That's the biggest. So in this problem, it's the number 4. So this is going to simplify, kind of like I showed you in the very first couple of examples, to 2 square root of 13. And so that's the value of the hypotenuse. We will no longer be accepting decimals in these problems unless otherwise specified, so we want you to simplify the radicals. All right, so let's go ahead and use the Pythagorean theorem since you probably have a good handle on it now, and we're actually going to find the area of a triangle based upon that. So what we want to do first is, like I said, we're identifying, we need to find the height because the area of a triangle is 1/2 base times height. And so what I know from this is that the base of this triangle is 30, and this height, it's from an isosceles triangle, is going to be a perpendicular bisector. So what that means is I'm going to go ahead, let me erase what I got up here. I'm going to split, when I draw the hypotenuse or the height in, it's going to split that bottom part in half. And so this piece is 15 and this piece is 15. And what I'm seeing here now is I have myself a right triangle. So I'm going to solve for the height using the right triangle right there. So using Pythagorean theorem, the height is one of the legs because 18 is our hypotenuse. It's across from the right angle. I'm going to square it, subtract it. Again, I don't have a perfect square here, so I'm going to simplify my square root. 9 is the biggest perfect square that goes into it, so I get 3 square root 11. If you need more practice with simplifying radicals, please let your teacher know. We can give you some more examples with this. All right, so now I've gone through and I've identified what the height is. So let me erase what I have now on here, and I'm going to redraw. So I know now the height is 3 square root of 11. And again, we're not bothering with any of that anymore. We're going back to the fact the area is base times height. And so when I'm trying to figure that out, I don't want to use the 15s. I want to use the 30 now. So let's find in the area, it's 1/2 times the base is 30, times the height is 3 square root of 11. When I multiply them through, 30 times 1/2 is 15, times 3 is 45 square root of 11. Okay, so that's how that's going to work. So here's another one for you to try. Why don't you hit the pause button and try it on your own. Okay, let's see how you did. The area of this one, you should have gotten the height was 24, nice perfect number, and the area was 240 meters squared. If you didn't get it correct and you want someone to walk through that with you, please let your teacher know. All right, so in some cases, I think you're noticing already that there are some that have perfect squares and some that are not perfect squares. And I'm talking about where the radicals in the answer and not. And what I want you to notice is that if you have 3 integers and everything is going to be a integer, there's going to be no decimals, those are called Pythagorean triples. And so we have some very common Pythagorean triples that exist, and that's these guys here listed at the top. So 3, 4, 5 is probably the one that you should memorize. That's the one that's going to be used the most throughout the year. But the other ones are also valid for you to use. It's okay if you don't get these memorized. It's just sometimes really helpful for you to notice that they exist. But what I want you to also know is that if you were to multiply them by 2, that is also going to be a Pythagorean triple. And if you multiply them by 3 or by anything. So all of these are our possible Pythagorean triples that can use. If you had noticed in the previous one, we had the 240, so it's that guy. No, that should have been just 24. In that previous one where you were trying it on your own, so the height ended up being 24, and it was probably one of these guys right here. All right, anyways, let's go ahead and move on. What we know here is that the Pythagorean Pythagorean theorem helps us solve for a side, but what we can actually do is take a look at what happens with the Pythagorean theorem when we look at acute or obtuse triangles. So this is an acute triangle. All the angles are less than 90, so we know that's acute. And let's go ahead and put it where 8 is the biggest one, so we're going to put it in for c squared. And so I get c squared, and then I don't know, a squared plus b squared. So I'm going to square the numbers out, and let's see what the relationship ends up happening. And I get 64 and 85. What I'm noticing here is that the c value is less than 85. So now let's take a look at an obtuse triangle and see what happens with that one. So in this case, 38 is across from the obtuse angle, so that's what's going to go in for c, because we always put the largest one in for c. And so when I square those out and add them together, what I'm noticing now is c squared is bigger than the a squared plus b squared. And this is always going to happen with this. So the converse of the Pythagorean theorem, if we were to substitute the values in, if the c squared is equal to a squared plus b squared, it's a right triangle. If it's smaller, then it's acute. And if it's bigger, then it's obtuse. This is a really good thing for you to have written down right now. So please make sure you get written that into your notebooks right now. Okay? So again, notice how everything is based upon the c squared relationship to determine what type of triangle that exists. So really quickly, what I want to do, at least one of these here, we want to determine if they form a triangle, and if so, is it acute, right, or obtuse. So remember, when you're doing these to figure out if they form a triangle, is you add any two sides and make sure it adds up bigger than the third. So looking at the first one here, 9 plus 15 is bigger than, I converted this into a decimal to 17.49, and you can just type this into your calculator. It should be able to convert that to a decimal for you. But moving on here, so what we want to do is substitute our values in to our Pythagorean theorem, and what I see, one of my see here is what's going to happen with the c squared. And so 3 squared of 34 squared is 306, 9 squared and 15 squared is also 306, so that means this guy here is equal. And so from there, we know it's a right triangle. Taking a look at the one on the right, letter B here, okay, the first thing we want to know is, does it form a triangle? And if you add any two sides, it does. So it has to be bigger than the third side. So substituting it in, we would have 26 squared with a c squared, and then 22 and 13 for a squared and b squared. And we get 676 and 653. And so what I'm noticing is that it's bigger. And so in that case, it's obtuse. Why don't you go ahead and try the next two problems. Okay, so for letter C, we should have gotten the two things were equal, and that's a right triangle. And for letter D, you would have found that it's smaller, so that's an acute triangle. And so that's the process. First, check to see if it's a triangle, then go through and substitute the things in and see what the relationship is to c squared. The last thing I want to do is a word problem with you. These are very common word problems. How high up on the wall will a 20-foot ladder reach if the foot of the ladder is placed 5 feet away from the wall? Whenever you're doing this, you need to create a visual for it, and we know it's a right triangle. So on the right-hand side, we have the wall. Along the bottom is the distance from the wall, because this is the actual ladder. So the distance from the wall was 5 feet. The ladder itself was 12 feet, and we want to know, well, how high up on the wall it's placed where the h is. And so we're going to go ahead and substitute all this into Pythagorean theorem. I'm solving for a leg. And so it's a squared plus b squared, or h squared plus 5 squared, and that's equal 20 squared. Square everything out, subtract it, and take the square root from there. And we want to make sure we're simplifying the radical. We're not just taking the square root of it. And in this case, it's 5 squared root of 15. The last thing we want to do is, again, one more. Actually, we're going to head and stop this since it is getting quite lengthy. If you want to take a look at this, I will go ahead and put the things through. This should be the last example for you to take a look at. But essentially here it's talking about a flagpole that's cracked. So this is the height of this piece that's still standing. It falls down. And this is the fallen portion. I'm trying to find, well, what was the original height of the flagpole there. And so if you did the Pythagorean theorem, you would have found what this fallen portion is, and we want to add them together. But again, take a quick look at this on your own time. I'm going to go ahead and stop this so that it doesn't get too long for you. I know it's already almost 15 minutes. And let us know if you have any questions about the Pythagorean theorem. I'll see you later.